Okay, so welcome everyone. Thank you for joining this seminar. Today, we are pleased to host Dr. Rob Siddall, who is a lecturer at the University of Surrey in the UK. And Rob's academic path started at the University of Cambridge and continued at the Imperial College London, where he received his PhD, and also continued at the Max Planck Institute for Intelligent Systems. His main research topic is robotics, and in particular, he has focused on robotics, or in particular, using robots to understand animal locomotion, which I guess is the topic of today's talk. I would like to mention that Rob has recently published a book on this topic, edited by Springer, so I cordially invite you to have a look into it. I just remind you that this talk, again, is going to be recorded, and we will have a question and answer session at the end of the talk, which is expected to last around 45 minutes. So without any further ado, Rob, the floor is yours.
Okay, thank you. Yeah, so good morning, everyone. I'm pretending like I'm in America, even though it's afternoon here. So my name is Rob. I'm a lecturer in robotics at the University of Surrey. And today I'm going to be telling you a little bit about some flurry of papers I published last year on geckos and other sort of small animals and how they move through the rainforest. This is work that was mostly done while I was a postdoc with my sort of co-authors, Greg Burns, Robert Full, and Arden Yusufi. So quick background, just to sort of give you an idea of where I'm coming from. So I did my undergrad at the University of Cambridge. I was an aerospace undergrad. I did my thesis on granular flow fields like this. I then went to Imperial College, where I spent a lot of time building some fairly wacky machines that flew out of water. I spent a couple of years developing an unusual UAV that killed weeds as a startup company. And then, after getting closer to nature, I ended up being a postdoc as a biologist, looking at geckos in Germany. And that involved, lots of trips to zoos, lots of analyzing animal data. And now I am a lecturer at the University of Surrey, where I'm sort of bringing back in the robotics a lot more, but carrying the same vein, still looking at animals, and still. I'm going to apologize here because there's someone in a room nearby drilling. There's not much I can do about that. Yeah, I'm very sorry. I guess it's my neighbors.
Don't worry.
Yeah. You'll be 5 minutes to go and yell at them, or anyway. So I'm talking today about gecko. Okay. Yeah, very sorry, everybody. So I'm talking to you today about geckos. So these animals they're tiny little lizards, but they are some of the most remarkable sort of examples of locomotion in the animal kingdom. So they can run on water, they can climb up walls, and they've been being researched for about a decade or more by a lot of people at the University of Berkeley, who are my co-authors on these papers we're talking about. So geckos are most famous for their sort of sticky toes, which allow them to cling to all kinds of surfaces and climb up vertical walls and ceilings. And they can run vertically up a wall about as fast as they can climb, about as fast as they can run on ground. So they're really, really fast. And they're very agile. So here you see a gecko running across a bit of a slippery patch, and it's able to recover itself and start climbing again in fractions of a second. When they're running across leaves, they can hit the edge and they can just flip right over and carry on running on the other side. If I can show you that from the side. So they run right up the edge, grab them with their toes, flip over, and carry on running. And they'll even run on water. So if you put them on water, they will run across the surface of the water about as fast as they can climb up a wall. And what they're doing there is a mixture of running on water and swimming at the same time. So they're both swimming with their tail and running with their feet, and sort of mixed mode locomotion. And perhaps one of the most impressive things that they've been seen doing so far is being dropped in midair. So this is a gecko falling off of a platform upside down, and you can barely see it, but in about in a fraction of a second, it flips itself completely over, and it's now in a nice sort of skydiving posture for landing. So all this work was done by some really great people at University of Berkeley in California. So I came into the picture a couple years ago when I was a postdoc in Germany, and what we had was a bunch of data from wild geckos in Singapore. So these are wild caught in a national park in Singapore, and we were watching them sort of glide between trees. Now, rainforests, you can sort of see here, very dense canopy, lots of stuff in the way, very hard to move. Predators on the ground, predators in the sky. So loads of animals have evolved very unusual kinds of flight. So you see ants that can glide, frogs that can glide, lemurs that can glide in Madagascar, lizards that can glide, even snakes that can glide. And the gecko we're talking about here doesn't seem really that adapted for gliding, but when you give it a chance to move between trees, it will jump and it will glide reasonably handily. So what you're seeing there is a gecko that's been released onto a perch on top of a tree, and it sees a tree about 6 meters away and it makes a jump. You can barely see it there, so I'll sort of highlight it. And we recorded geckos doing this about 30 times. So jumping off of a platform, picking up some velocity, then transitioning into about a 45-degree glide and hitting the tree. And they're doing this about 6 or 7 meters per second. What you're seeing here is the product of me clicking about 10,000 video frames in order to get these geckos. And what we observe is that they are coming into the tree still accelerating most of the time. So they're not really slowing down. On average, they're slowing down by about 5%, which is very different to what you usually see in gliding animals like your flying squirrel or your flying lizards. And when we look up close at what's happening, you can see they're sort of just crashing headfirst into the tree, barely slowing down at all. Yeah, so there's another example. And we can look at sort of the data up close, and we can see that there's a slight increase in pitch. So they are preparing to make the impact, but they just have no ability to brake. Unlike all these sort of specialized gliders, they don't have the wing area to really decrease their speed in any significant way. So what they do instead is they land headfirst, and they've sort of invented this maneuver which allows them to slow down gradually. So if you slow down, you take an impact full in the face at 70 meters per second, you can either absorb that with friction, your tissue, or with further motion. And so what they do is they sort of take the impact on their face and they roll down the tree, and sometimes they'll flip completely over. And so we've analyzed that up close, and you can get sort of ideas of angular velocities, that kind of thing. And we even see that a few of the geckos that were caught wild, these geckos can all drop their tails whenever they want to escape from a predator, and they'll regrow them slowly over time. So several of the geckos that were caught actually were missing a tail. So when those geckos tried the jump, they can still make the glide, but when they reach the tree, they couldn't hold on. So at this point, we're kind of curious to dig a bit more into how they're landing and making this impact. But there are some pretty big challenges there. So if I go back to the video, here is a gecko gliding. So you sort of see kind of how big it is there and how much distance it's covering. So the prospect of having that gecko land on a force sensor or any kind of sensorized platform is not very good. You could try have a sensorized pole, but we want the gecko to glide willingly to the tree, and so it needs to be a tree that looks like something you would want to land on. And you sort of see the landing up close here. It's very, very small. So this gecko is about 10 centimeters long. They weigh about 3 grams. So there's not much prospect of adding sensors to the gecko either. So there's not really a lot of ways in which we can get any meaningful measurements about this landing other than videoing it. So the solution was to just build our own gecko. This is what we did. So you have here a robot gecko. So it's made of rubber materials. It's got movable legs. It's able to sort of move its tail up and down to sort of mimic some of the actions of the gecko. And it's got a sensor built in so that it can detect the landing, which is enough for us to basically recreate the gecko sort of like landing on the tree. One thing geckos have, which our robot doesn't have, is adhesive feet. So these feet here, they're covered in, millions of tiny setae, and replicating this kind of van der Waals adhesion is its own research area. So what we ended up doing was opting for Velcro onto a felt material. We went through a few different iterations of adhesives and stuff, trying to get something that had a similar adhesion force to the gecko, and we ended up with Velcro on felt. Now, actually, it's not Velcro on Velcro. The thickness is too good on Velcro. So what it is a kind of felt that we've shaved down. You can see there on the left is the adhesion force of our robot on the wall, and then on the right, that's just regular Velcro. So we've sort of Velcro, but much, much weakened. And it's been tuned to be about the same as the gecko landing force. So we built a catapult, and now we can fling our robot at controllable speeds, controllable angles onto a wall. And this is what it looks like when we play them side by side. So robot comes in, lands on its feet, grabs on with its hind feet, and just sort of passively performs the same maneuver as the gecko. Now, all of a sudden, once we have this robot, instead of people spending years trying to capture and film wild geckos in a rainforest, now in an afternoon, we can get loads and loads of landings. And now our video is higher quality, so we can use deep learning to do all the tracking rather than clicking videos endlessly. And straight away, we can see with our robot, with the tail, landing works well, but without the tail, not so much. And now, using this experiment, we can start rattling through lots of different landings. So we can, so we can throw the gecko at the wall 500 times, and we can see, how changing the feet, changing the landing, how changing the angle, the velocity, the tail behavior, and we start to build a picture of how this landing works in nature. And this is the output of that. So we have about 500 landings trying with and without the tail. And straight away what we see is that without the tail, the success rate drops dramatically, same as we observe in nature. But what we really wanted to do was get new data. So not just sort of the same positional information, same video recordings that we had of the animal. We wanted to try and add something to it. So we actually had the robot land on a force plate. Once we sort of dialed in the experiment and had the behavior we wanted. And so now we can see the exact force on the feet as the robot is impacting and holding on. And we can see that as we sort of shorten the tail gradually, forces get higher. And we can see that if we add some kind of active reflex where it senses the impact and then moves the tail, we get a much lower force than we do without the sort of like active muscle inside the animal. If you plot that on a graph, what we see is we've got a sort of 1/length relationship between the force needed to attach and the length of the animal's tail, which sort of confirms a lot of things you suspect about what the tails are used for. So these animals' tails, in lizards at least, are very versatile. So they're used for swimming, they're used for attachment when climbing, they're used for fighting, and they're very, very versatile appendages. And so this is just sort of one more example of what you can do with the tail. Now that's just the landing part. We also wanted to take a look at the gliding phase, which, if anything, is more interesting because it's a very unadapted animal, but still a very competent glider. So again, I return to this original slide of a gecko gliding behind a tree. And the gecko is sort of free falling for a bit and is gradually pulling up into a glide and is sort of holding a constant angle of attack as it approaches the tree. And for some of the videos, we had enough detail that we could sort of see how the gecko was flying. So in this example, we managed to put a sheet in the way so we can really get good detail on sort of the body posture. What you're seeing there is the body's angular velocity versus the tail's angular velocity. You can see the tails are constantly swishing as it's in the air. And then the graph below is a cross correlation. What we see is that the sort of cross correlation peak between the two is pretty much lined up. There's not really a time delay between tail movement and body movement, which is not what you'd expect if it was an aerodynamic effect, because you should have some sort of lag. And we wanted to kind of drill into that a bit deeper. Unfortunately, the robot we had was a bit big, so we had to scale it up for a few reasons in order to get the same kind of like material and sort of force behavior on the platform. But for flying tests, we would need to have the same Reynolds number and really be at scale. So we built a new robot, this time same size as the Gecko, same Reynolds number, and we replicated this sort of free fall behavior of the animal, a bit slower, purely because we didn't have a second story launch platform. We had a 4-meter high lab to work with, and so it's a bit slower when we're recording it, but the robot's slightly bigger, which means the Reynolds number is about the same. And so straight away we can see, yes, the tail is having a big aerodynamic effect. Just from dropping the robot with different fixed tail angles, we can see that, yeah, you get an aerodynamic torque on the robot as it falls. So now we try and look at all these sort of minor tail swings that we observed in the animals. So here are some examples of tail movements mid-flight. And what you see is that, yes, there's an immediate response from the animal body, from the inertia of the appendage, and then a slower aerodynamic response. So looking at our data, it looks like these tails are being used inertially, so like a reaction wheel on a satellite, rather than like as an aerodynamic rudder, as you might see like on a plane or a bird. So to get a bit more detail on that, we actually went back and looked at some old experiments from about a decade ago by my postdoctoral supervisor, Dr. Yusufi. So when he was a PhD student, he had put geckos in a wind tunnel. What you're seeing here is a vertical wind tunnel with a mesh there, and a gecko flying. You can see the wall of the wind tunnel has been painted to give a loose appearance of a forest canopy, so that the gecko tries to move across the tunnel as if it were gliding between a tree. So here you can kind of see up closer the posture it's taking while it's in the air, and you know how it's kind of like controlling its flight. And for scale, there is a researcher, and there is a gecko. So just so you get an idea of what's going on here. And some of the motions we observed while it's in the wind tunnel were repeated yaws of the tail. So the gecko would often try and reorient itself in midair to face a different direction, and it would use its tail to sort of swing itself around inertially. Go back. Yeah. So tail swings around, body swings the opposite way. You get sort of zero angular momentum reorientation. And that's really easy to model to see, like, sort of, you know, how much force you would get from doing that. So here are 4 different models of a gecko swinging their tail, and you can see that, yeah, you would get, the tail is massive enough that you would get quite a significant yaw just from swinging it around. We can sort of look at what kind of tail length might be optimal for that. So here, you see you can get up to about a 90-degree yaw if you get a big enough tail. Gecko tails are about the same length as their body, but a lot of lizards have much bigger tails. You know, as many as 5 times their body length. If we look at how effective that is as a way of orientating, you get diminishing returns on maneuver speed the bigger your tail gets. So here are sort of a few examples of different animals, lizards with different tails, and you can see that. So you get quite a lot of diversity in tail size. Geckos are usually about the same length as their body, depending on how recently they've shed them and how much they're regrowing. There's actually an optimum tail size, which you can get from looking at this, which is about 4 times body length. But at that point, this imaging gets a bit unphysical, so we're sort of ignoring that part of the graph. One problem with looking at the tail in this term is that it's a reversible movement. So inertial reorientation is reversible. So if you swing the tail one way, you gotta swing it back the other way. Otherwise, you can't keep your tail forever. And so all your inertial movements are going to result in zero net motion. So what's actually happening is a bit more complicated than that. If you look at, here's an example of a gecko trying to move itself on a wind tail, and you're seeing is that there's several axes of motion for the tail, not just straightforward yaw. So took the same model, and we did some sort of did some trajectory optimization. So sort of classic robotics approach. You want to achieve a certain output motion with an input appendage. You sweep through trajectories and try and find one that does that for minimum effort, minimum control effort, minimum energy. This is what we did. So we swept through a variety of tail motions and tried to find one that gave us the orientation we wanted. What we found was, so this is a trajectory, found by a genetic algorithm for a gecko in free fall. Now, the important thing here is that this is a gecko in 0G. There's no aerodynamic forces here. So this motion is not really anything that you would see in a real animal. It's sort of figure-8 motion, which is not really very physical. So here's that kind of motion, which is not anything you'd ever really see an animal do. So we sort of realized we needed some external forces in here. That it's not just this is not happening in a vacuum. Even though we're seeing inertial effects, it's not a purely. You can't just ignore the aerodynamics here, obviously. So looking at kind of the rough kind of forces the gecko would experience, we can get a very basic approximation for our model, just using, a spring model. So think of it as similar to linearizing the equations of motions of an aircraft around the sort of center. So we're basically approximating the aerodynamic effect as SHM around each axis, so harmonic motion. So we have, springs in roll and pitch, but not in yaw because it's falling vertically down, so there's not as much of a yaw torque. And so now, once we had those forces and we sort of tuned them to be roughly the same as aerodynamics, when you do a trajectory optimization, what you get is very similar to the motion you'd expect. And it's about the same as what you observe in the animal. So it's big, sort of wide swing, tail high. So the tail moves in plane, then moves over 90 degrees and backwards and forwards. So now we want to sort of see, okay, well, which is the one that matters for the animal? So you can get a reasonable estimate of the aerodynamic torque on the gecko by treating its appendages as cylinders. So we have good measurements for all of the various legs, tails of the gecko, and we know that they're falling at pretty consistent speeds. So we can get a reasonable approximation of their behavior, of the forces on them. So we look at the aerodynamic torques they're getting. So the force generation capacity of their legs is about 37 million Newton-meters. Compare that to a tail put all the way out. So the maximum roll torque you get there is about 4 times as much, 3 times as much. So the tail is having a much bigger effect aerodynamically. And in terms of inertial torques, we need to know, for inertial torques, we need to know how fast the tail can accelerate. The inertial torque is essentially a reaction torque. So how fast you can move your tail is how much torque you can apply. So we can get the acceleration from looking at all those sort of like rapid tail oscillations that we saw as they were falling. And we could get a rough estimate of the inertial torque on the animal. And what you see is that the inertial torque is 380 millimeters, so quite a lot bigger than the aerodynamic torque. So what this sort of tells us is that for the gecko, if you're trying to make quick corrections to your body posture, inertial forces are what you rely on rather than aerodynamic forces. And that's kind of borne out by their size, their velocity. So you see geckos free falling at about 6 meters per second. And what we see is that that's the speed at which aerodynamics start to matter more, but inertial forces still matter a lot more. Inertial forces are basically independent of speed, so you can always use an inertial reaction force, no matter how fast you're falling. But you need to have a certain velocity before you can start to develop useful aerodynamic forces with your appendages. And so what we see is at low velocities, lots more tail motion, which is why when they're falling down, you see lots of tail motion. And then as they speed up, you see less tail motion, more small corrections with the appendages. And that's kind of borne out by observations of, like, so this is the earlier example of a gecko falling upside down off a plate. You see that, so the velocity is starting at 0 here. So it's using almost entirely inertial forces to reorient itself. It's not relying at all on aerodynamic sort of light steering. High velocity, inertial forces dominate. And this is not going to be constant for all sizes. It's going to be very scale dependent. So we can get a rough notion of how these forces will scale by, just a sort of fairly coarse analysis. You can estimate that the aerodynamic torque of, just a rod as you're free falling is going to scale roughly as length to the 4. So you've got a force times a length and a velocity. Your velocity will scale with your mass because you're in free fall. Whereas inertial forces, essentially, it's just a muscle torque. So how much torque you can apply through inertial forces or how much torque you can apply with your muscles. So how strong your muscles are or how much torque you have. So it ends up being area times the length, so length of the cube. So what you see is that aerodynamic forces are going to become a lot more important as you scale up your animal. So for small animals, inertial force is very helpful. For larger animals, inertial forces start to drop off. And that's very much borne out by what you see in nature. So here's an animal that is, 20 times bigger than a gecko, but still very acrobatic, does a lot of sort of jumping between trees. This is a squirrel. So in a squirrel, the tail only weighs about 1% of your body mass, rather than 10% in geckos. But in lieu of mass, they have adapted to give it a lot more aerodynamic area. So it's very, very furry, effectively. And that fur, the fur area gives you a very effective sort of aerodynamic surface, even though it may not look like it to, aerospace engineers. And we're actually sort of looking at that in a bit more detail. So this is an experiment, YouTube video that came out a couple of years ago. I would not condone this ethically, but it does have some very interesting animal behavior. So you see there the squirrel's tail moving in that kind of circular motion. So it's both having an aerodynamic effect and an inertial effect. And we are trying to take all these kind of like rough modeling simulation work and turn it into hard data. So we built ourselves a robot with a 2-axis tail. Essentially, it's something I put together out of a camera gimbal, but we now have a tail that can move with 2 degrees of freedom quite quickly. And we've got some preliminary experiments. So you can see here we've taken the robot and given it a flick, and it's turning on its tail, and it's using that tail to absorb all that angular momentum it has. So we throw it with a lot of roll motion, and using its tail, it can slow itself down. Yeah. And the next stage is going to be to take that tail and vary its length, vary its area, and play a lot more with the actual control approaches. So we can start to drill into what's actually going on. These very complicated animal motions. And we're building, because we're sort of interested in the squirrel angle, we've been looking at some unusual flying squirrels, which probably no one's heard of. They are they're very rare. So it's me holding one there. They are called scaly-tailed flying squirrels. They're not actually squirrels, but they are rodents. But they are unique in that They have flying membranes, as you can see there, but they do not have the bushy tails that you see on every other squirrel, every other flying squirrel. Instead, they have very, very thin tails, and they have spines. So they're one of the few mammals that has spikes. So that's the underside of its tail. So that has implications both for how it lands and for how it moves in the air. And so we've got the beginnings of a robot prototype, and we are also catapulting these animals around. So sort of coming on to now where we're going with this. So you may have seen the catapult we used to launch the landing was made of mostly MDF and latex. It wasn't the most accurate thing. So we've designed a new catapult. So what you're seeing here is a much more powerful, much more accurate machine that can launch things at a variety of angles and up to about 30 meters per second. So that was designed with my colleague Raphael Zufre, who you should look up if you're interested in this kind of stuff. And we are building better robots. So we're going to try and drill into a variety of different flying animals, so not just the gecko. So we're looking at flying geckos with actual wing membranes. And we've built robots. We've got sort of a basic robot platform design that now is active. So we can move the tail in the air, has sort of like wireless connectivity with flight system, IMU on board. So now we can both get motion capture data, acceleration data, real-time control. So it's going to be a much more sophisticated flying experiment. And we're going to be launching them across the room at a variety of speeds, and it's going to be fun. So I've got through that a little bit fast, but that's kind of like a flavor of what I'm doing right now. I spent the first part of my career building robots using nature as like a source of inspiration. So you've got here, a drone that bursts trees, a aircraft launches stuff out of water, and we sort of like would look at the biological literature for ideas for how to make interesting robots or how to deal with locomotion challenges. And what we're doing now is sort of the opposite. We are building robots for the express purpose of understanding nature better. So these are no longer robots for service. They are robots designed to be model animals to contribute to biological literature. It's something I really like. You often see these kind of chaotic utopian visions of robots mixed in with the city, monitoring our systems and fixing our stuff. And I like to imagine that in that future that the robots are, we're not just using nature to build ourselves cool replacement robot nature. We're also using our robots to give a little back to nature. And if that kind of thing interests you, myself and some colleagues from universities around Europe are putting together a robotics contest. And the idea is that we are going to be building robots based on designs submitted to us by anyone who wants to. So if that's something sounds like you'd be interested in, get involved. We're looking for judges and other people to be involved in the magic submissions. And with that, I will say thank you. I've gone a little bit fast with this, but yeah, if anyone has any questions, I'd be happy to answer them.
Thank you very much, Rob. No worry about time. We'll have more time for questions. So you're welcome to turn on your microphone or just write down in the chat as you prefer. So any questions?
Hey, Rob, do you mind if I ask a question?
Sure.
Sorry, I just called you Rob. I actually don't know if that's what you go by, but so I was just wondering, yeah, can you tell us more about the self-riding squirrels? So I know you kind of went by that pretty quick, but it does seem surprising, given how light their tail is, that they have enough muscle force that you would consider the inertia significant. Would you be able to comment on that, or is that someone else's work and you don't want to go in there?
No, I mean, it's just you can move fast enough, and you can get the. It's surprising. You wouldn't think so. The gecko, it's obvious because it's 10% of its whole body mass. But yeah, I mean, I can go back to the video. I think this tail here. is, if I can play this video. Yeah, the tail here is not 1% of the body mass. I think it's about 5%.
Okay.
No, maybe a little bit less. But you know, the tail turns on, and it's quite quickly suppressing the motion there. The squirrel is able to do a lot of things to like sort of manage its inertia, so it could pull its body, its arms in and out. And it looks like it has a lot more inertia than it does, because if you shave a squirrel, it's a much skinnier looking thing. than, you know, it's still kind of early days for the more complicated motions. So we're still kind of like messing with the robot and getting to do better stuff. But yeah, does that help?
It does, and I think it's useful. I've been pondering flying squirrel flight as well, and have done no work on it, just pondering it. And so it's kind of cool to see that all those tail motions that do happen in like YouTube videos, they're not just going to be aerodynamic. They might have a significant inertial contribution based on at least this. Yeah.
Yeah, I mean the tail obviously has got quite a big aerodynamic area for its weight. But that's why we want to look at these flying squirrels from West Africa. But they are extremely rare. Like, you know, the kind of rare where they might be extinct by the time you manage to see them. So right now, all I've got are like 3D scans from natural history museums. That's not much to go on in terms of animal behavior. But.
Cool. Thank you.
Okay.
Any other questions? If not, meanwhile, maybe someone. Yeah, you can go. Yep.
I can throw out another one, which was just something I was trying to make sense of.
Okay, yeah, we have time. Yeah.
There was, I might have missed this. You were showing different optimizations for, I think, producing a yaw in the body, inertial optimizations. Correct?
Yep.
What shocked me is, isn't just yawing the tail optimal? Why would you need to do anything other than just yaw the tail to produce an optimal body?
Yeah. So the constraint is it has to start and finish at the same point. Yeah. So in all optimizations, the tail starts perfectly parallel to the body and finishes perfectly parallel. But the idea is that it has to be something you can do twice. Right. So you can't just swing your tail around and then forever be an L on the whole rest of your flight.
Okay. No, that's so much cooler. I didn't realize that. Okay, that's really awesome. Because inertia. So if I'm thinking about what I know inertially, we've got bats do a lot inertially, birds do a lot inertially. These guys, these lizards do a lot inertially. It really does seem like inertia is this huge maneuvering complex that we need to take advantage more in our robots. Yeah.
I mean, absolutely. Yeah. I mean, it does kind of fade away as you get bigger. I mean, it's worth sort of like, you know, saying here that the very first birds have big long tails, and birds now have essentially massless tails. You know, they're
they're using their limbs, I think, like bats and birds. Swinging around their wings. Cool.
Actually, I have a curiosity about because so you mentioned about the material, like for Velcro. Does this choice depend also on, say, the material of the landing site? So, for example, if you test this with wood, or if you test this with, I don't know, plastic or whatever it is, you know what I mean? So, if you test like a Gecko for landing in a piece of wood, or landing in a piece of plastic, or in a piece of metal, I don't know.
I mean, in all cases, we're landing on a rigid platform. I mean, it's a piece of wood.
Okay.
But yeah, I mean, we didn't really look into like making the surface soft at all. I think that was just sort of adding too much complexity for.
The point here is actually if the behavior changed according to the material or not. The landing material. I mean, the material of the landing site, I'll say.
Okay. So I would basically let me just do it from here. Yeah. So the behavior didn't really the behavior of the sort of the rolling back and then the recovering that only comes when if you have too strong attachment, it just sort of grips on, and what it'll do is it just sort of gradually destroy the surface, and you absorb all the force by like ripping off the like abrading the surface,
Yeah.
which would correspond to like ripping your skin off, or or damaging your claws. And if you make it too weak, you just fall off and you fall down. So there's kind of a sweet spot where you can hold on just enough to like take out a little bit of force, and then you're slow enough that you can slow down by rolling down the tree, basically.
Okay. Yeah. Any other question? There are no more questions. Okay, so yep. Anything else?
I was just
okay.
gonna wave
Great.
by.
So I'll stop sharing. So thank you everyone for joining this session.